Hi folks, welcome back to Physics with Captain Rod. I'm making this video to help you out with number 17 in your homework. I want to say this is 17 if you're in my Physics 112 class. It is number 20 if you're in my 222 class, and it is in fact the same problem. Okay, so let's see. This 10-gram particle released from rest in a uniform 500 Newton per Coulomb field. So here we get this particle here, and it's in this 500 Newton per Coulomb field. So this is going to create a Coulomb force. Put that force vector on this picture. That comes right from the direction of the electric field. The electric field direction is given here with these arrows. So that should tell you the force direction. And here's how it's calculated. All right, the electric field is defined as force over charge. Now, very much like the gravitational field is defined as the gravitational force over mass. Notice we calculate a gravitational force by mg. Well, you do the electric fields the same way. You calculate a Coulomb force by taking charge times electric field strength. Now, you might wonder, do we need to worry about a gravitational force? Well, this is what I would encourage you to do. Calculate. Give me just a moment here to think about this for a minute. mg. Actually, to tell you the truth, they're going to be kind of comparable here in this problem. I did not intend them to be. This says calculate the Coulomb force, which I just talked about how to do. And then I want you to find the acceleration. And I had intended this to be not gravity being an example. Just imagine that is the only force acting on that particle. Probably reword this in the future. So assuming that is the only force acting on it, calculate the Coulomb force and then the acceleration. And the acceleration you get from Newton's second law. Force equals mass times acceleration. And again, you've calculated that. Mass is given in the problem. Okay, part B, where it says to sketch a velocity graph. Right? So this particle started from rest. This is now a physics 1 type of question. So a velocity graph might look something like this. Velocity against time. Assume it starts from rest. Put a point on the graph. And then sometime later, it's going to have some velocity we don't know. Put a point on the graph for it though. Right? And that distance is your v of t. Now, to find that function, there's a couple ways to do it, but this is a linear function. And the acceleration, remember, is equal to the slope of that line. That should allow you to find that function, no problem at all. Okay, part C, where it says calculate the kinetic energy after it has moved 5 millimeters. So here's what I mean, or here's what I'm getting at. All right, now we're going to start talking about how energy principles play into all of this. So we have this particle at position 1, presumably starting from rest, or I had intended it to. We know that there's a force acting. You should have it hopefully in this direction. And this is a number that you have calculated. And this particle then accelerates over this distance. So from a work energy standpoint, there's work being done. If I write out the work energy theorem, PE1 plus KE1 plus work equals PE2 plus KE2. Now, how you take forces into account is up to you. We're going to be assuming there's only one force here, and we're going to use a work term to do it, and we're not going to worry about the concept of potential energy just yet. So long story short, don't worry about this, this, or this. That should tell you how to find the final kinetic energy equal to the work done. So that should be enough to get you through that problem. I'm going to stop that right there. Have a great day.